Chapter 5.1, Systems of Linear Equations. A set of linear equations is called a system of linear equations. The solution to a system of linear equations must satisfy every equation in the system. Thinking of the graph of a system of equations may help us understand what it means to be a solution to the system. So let's just start with something very basic. 2x plus 3y equals 6, and perhaps y equals x plus 2. Okay, I cannot solve either of these equations independently because they have an x and a y. There's an infinite number of combinations of x and y that will satisfy these. And we know that those combinations form a line. So I can graph each one of these as a straight line. This one's set up perfectly to graph using the intercept method. In other words, if x is 0, then y is 2. So there's 0, 2. If y is 0, x is 3. Once I have 2 points, I can hopefully draw a straight line through those 2 points. And what that means is every point on this line is a solution to this equation. This equation is set up perfectly for the slope-intercept method. I know that the y-intercept is 2 and the slope is 1, which means up 1 over 1 is another point on the line, and down 1 backwards 1 is another point. Once I have at least 2 points, I can connect them with a straight line, and every point on this red line is a solution to that bottom equation. To be considered a solution to the system of equations, it has to be a solution that satisfies both equations at the same time. And notice this point right here is on both lines. So the point 0, 2 is my solution. In other words, if x equals 0 and y equals 2, that's a solution to this system. Thinking about graphs also helps us understand everything that can happen with a solution to a system. One thing that can happen is the two lines intersect, right? They intersect somewhere, and that one point where they intersect is the solution. Or another thing that could happen when I graph my lines is that I find out that they're actually parallel lines, meaning they never intersect, meaning there is no solution to that equation. There is not an x, y value that would satisfy both equations. No solution to that system. Or, when I graph my lines, I could find out that they're actually the same line, which means there's an infinite number of solutions to the system. Any combination of x, y values would satisfy the system. And we'll talk about how to leave our answers for that as we get to it. Notice that since these are lines, that implies they're straight. If it's not straight, it's not a line, right? That means they can only intersect at one point, right? Two lines can only intersect at one point, meaning we can get away from graphing the systems to find a solution. The reason we started graphing was because we had these infinite solutions, right? But if I'm back to having one solution, I don't have to graph it. And really, that's great, because suppose my intersection was at a point like this. What is this? When x is 6 and y is negative 6.5? Negative 6 3/5? Negative 6 3/7? What if I just didn't draw my line straight? Is that actually supposed to be right here at the intersection at the grid coordinate between when x is 5 and y is negative 7? Or is it not? So graphing, not an ideal method anyhow. So one of the other methods we're going to look at is called substitution. Here's your steps for substitution. But basically, I'm just going to substitute into the other equation, because again, my problem with solving either of these equations is I have two variables. So I can't solve either one for a solution. But this equation tells me that y is x plus 2. Well, if I know that y is x plus 2, then I can substitute that into my other equation. So 2x plus 3, but instead of times y, because I know y is x plus 2, I'm going to put x plus 2 in for y. And then finish my equation equals 6. So here's the top equation. 2x plus 3y equals 6. But now this is an equation with only one variable. I can solve this equation, and it's a simple, basic linear equation. I'm just going to get rid of my parentheses. 2x plus 3x plus 6 equals 6. Combine like terms. 5x plus 6 equals 6. Subtract 6. 5x equals 0. Divide by 5. X equals 0. But don't forget, I've got to have an x and a y. So once I get one of the solutions, plug it into either of these equations. This equation would be the easiest place to plug it in. I know that x is 0, so just replace the x with 0. So my solution is x is 0, y is 2. The substitution method. And I can solve for any equation, I can solve for any variable in either equation. So choose judiciously which variable you solve for. Let's try that again. Okay, so over here, again, I'm going to solve for the y. Simply because I could solve for either equation, either variable in either equation. But if I try to solve for this x after I add y, I'm going to have to divide by 3. I just made a 1/3 y and a 4/3, and then I'm going to plug fractions into my other equation. So I'm going to try to avoid fraction. I may not always be able to, but instead, if I solve for this y, all I have to do, and I've got a couple of choices, I can subtract 3x from both sides and then get rid of the negative, right? Divide everything by -1. Or what I'm going to choose to do, I'm going to add y to both sides and then subtract 4. So I wind up with 3x equals 4 plus y, right? And then I can subtract 4. So (3x minus 4) equals y. Now, once I have one of the equations solved for one of the variables, I can plug it into the other equation. I have to plug it into the other equation, the equation I have not yet used. And so this would give me negative 9x plus 3 times y, but I know y is 3x minus 4. Finishing my equation equals negative 12. And I wind up with an equation with one variable. So I can solve that equation. negative 9x plus 9x minus 12 equals negative 12. Negative 9x plus 9x is 0. So I wind up with negative 12 equals negative 12. Remember that when our variables disappear, it's an indication to me that my solution is either no solution or infinite solutions. Okay? If I get my variable equals a number, then I've solved it and I go on. But if my variables disappear, I either get something that's true or something that's crazy. If I get something like this that's not true, I can never have 0 equals 7. That's my indication that my answer is no solution. But if I get something that's true, that's always true, what that means is no matter what I plug in for x, I'm always going to get a correct answer, that negative 12 is negative 12. Yes. So this is my infinite solutions. The way we're going to write our infinite solutions is we'll be told to leave one of the variables arbitrary, right? Let's just say they tell us to leave x arbitrary, and they could tell us either one. So if it's x that's arbitrary, it means I'm going to write my ordered pair with an x. If it said leave y arbitrary, I'm going to write my ordered pair with a y. Okay, then I'm going to take, now we're not doing this one, that's just, I could do that. All right, so pay attention to which variable they tell you to leave arbitrary. If they don't tell you, I believe they'll usually mean for you to leave the last one arbitrary. But we're going to leave x arbitrary. So then I take one of those equations, any one, it doesn't matter, solve it for y, because that's what I don't have yet, in terms of x. Well, I've already done that right here. I already know that y is 3x minus 4. So that's my y value. Y is 3x minus 4. I do not want to say, if I have two variables, that my solution is all real numbers, like we were saying when I have one variable. Because my solution, for example, is not, let's say, 1, 0. If I plugged a 1 in for x and a 0 here, that doesn't work. So all real numbers isn't my solution. Here are what my solutions look like. If x is 1, then I know that y is negative 1. If x is 2, I know that y is 2. If x is 3, I know that y is 5, etc., etc. I can find as many solutions as I need. Okay. We have another method called elimination by addition, or simply the elimination method, or simply the addition method. But technically, it's elimination by addition. It's based on the fact that we can add two equations together and get a third equation. So let's add two simple equations together that's very easy for us to see what's happening. If I add these together, I wind up with 6 plus 5 equals 11. Look, I have another equation that is true. So I can add two equations together to get another equation. The problem is it doesn't help us to get a third equation with two variables. In other words, I could add these equations together right now and get 7x plus 5y equals negative 14. And I have another equation that has the same solution, another valid equation. But it doesn't help me because I can't solve this equation either. So our goal in adding them together is to see that one of the variables gets eliminated so that we wind up with one equation with one variable, which then we can solve. Since I'm going to be adding them together, I want to make sure I write both equations in standard form so that I can add my like terms. I need my x's to be lined up. Excuse me. I'm going to take a break here and get a drink. I need my y's to be lined up, and I need my constants lined up. Okay. I can't just add these together. We just looked at that. But if I could change these coefficients or these coefficients to the same number, where one's negative and one's positive, when I add them together, that would eliminate that variable. Doesn't matter which one I eliminate, but I'm going to choose the y's just because it'll make my number smaller. So pay attention to whatever makes your math easiest. I'm going to multiply this top one by -2 to maybe change that -15 to a positive. So -2 times -2 times -2 gives me the equation -4x minus 6y equals +30. And if I multiply this bottom equation by 3, again, my goal is to make both of these numbers 6, one positive and one negative. Then I wind up with 15x plus 6y equals 3. And adding them together, I see my y's get eliminated. And I have 11x equals 33, or x equals 3. Now don't forget, I need an x and a y, but now I can plug into either of these equations and get my y value. I'm going to do it here where my numbers are smaller. The original equation, 5 times 3 plus 2y equals 1. So 15 plus 2y equals 1. Subtract 15. 2y equals -14. So y is -7. So x is 3, y is -7 is my solution. Okay, let's look at this one. Once again, I'm going to solve for y. Oh, wait. Sorry. I'm not doing the substitution one. We're already on elimination. Boy, time flies when you're having fun. So I need them to both be in standard form. I cannot add an x and a y term, right? I need my terms to be alike. So this one I need to subtract 6x from. All right, so this one I'm going to leave the same. I'm going to have 6x minus y equals -1. This one, if I subtract 6x, I'll have -6x plus 5y equals 17. And hey, look at this. I can go ahead and add them together as they are, and my x's are going to be eliminated. 6x minus 6x, 0. So 5y minus y, I wind up with 4y equals 16. So divide by 4, divide by 4. Didn't even know I could do that. Y equals 4. Once I know what y is, I can plug into either one of these equations and get what x is. I'm going to plug in to this one. 5 times 4 equals 17 plus 6x. 20 equals 17 plus 6x. Just solving a basic linear equation now. 3 is 6x. So x is 1/2. So remember, it's an ordered pair, so pay attention to the order you put your solution in. 1/2, 4 is my ordered pair, my coordinate. X is 1/2, y is 4. Okay, now let's look at equations with 3 variables. The first thing I want to make note of is if I have 3 variables, I have to have 3 equations. Remember, on the 2 variables, if I had 1 equation, I couldn't solve it, right? That's when we graph the line because there's an infinite number of solutions. But when I had 2 variables with 2 equations, hey, I could solve it and get 1 answer. Okay, same thing here. If I have 3 variables and 2 equations, I know immediately it's an infinite number of solutions. If I have 4 equations with 3 variables, it's an infinite number of solutions. If I have 4 variables, I have to have 4 equations in order to be able to solve it. The only difference is 3 variables make planes instead of lines. So we have the same 3 options. Those planes can intersect. Those planes could be parallel, or those planes could be the same plane. With a system of 3 equations, we're going to use a combination of our substitution and elimination method. Okay, the first thing we want to decide is which variable we can easily eliminate from all 3 equations. The biggest mistake people make is they take these 2 equations and eliminate the y, and then maybe they take these 2 equations and eliminate the z. I have to eliminate the same equation both times. So I'm going to take 2 equations at a time and add them together and eliminate one of the variables. Doesn't matter which variable. I'm going to choose the y's on this one because I notice, hey, I can add these together without doing anything. And the y's get eliminated. And then if I choose these 2, it's a one step. All I got to do is multiply by 3 and they get eliminated easily. So first thing is I'm going to take these 2 equations and just add them together as they are. So x plus 3y plus 4z equals 14. 2x minus 3y plus 2z equals 10, because when I add them together, these y's get eliminated, leaving me 3x excuse me, plus 6y equals 24. Hey, when I see something like this, I want to pay attention. As long as I have an equation, I can make these numbers smaller, right? So if I divide everything by 3, I can come up with an equation that says x plus 2y equals, oh, it's not y. Boy, don't make that mistake, guys. I eliminated my y's. I eliminated my y's. This is 3x plus 6z. So x plus 2z equals 8. All right, now I've got to use this equation because I haven't used it yet, but I can use either of these. And I could use these 2, but that would require multiplying this by -3, and you know, signs is where we have the issues. I don't have to worry with a sign here since they already have opposite signs. So I'm going to take these 2 equations and multiply this one by 3. That means I have x plus 3y plus 4z equals 14, and 9x minus 3y plus 3z equals 27. Don't forget to go all the way across. with whatever you're multiplying by. All right, so I wind up with 10x plus 7z equals 41. Now I have two equations with two variables, the same two variables. So the rest of it's just like what we were doing on the previous slides. And notice how much easier it's going to be to eliminate a variable with this equation instead of this equation and this one. Look how big my numbers might be getting. But here, because I wound up with a 1x, if I multiply this by negative 10, right, so I'm going to multiply this equation by negative 10, by negative 10, by negative 10, giving me negative 10x minus 20z equals negative 80, and add it to this equation of 10x plus 7z equals 41. Then I wind up with negative 14z equals negative, oh wait, can't add for some reason right now. 20 minus 7 is 13. Negative 13z equals negative 39. And I worked it down to one equation with one variable, so I know z is 3. Now, before we went back to our original equations, but it wouldn't help me any to plug a z into one of these equations. I'd still have a variable, an equation with two variables, so I couldn't solve it. But I can plug it into either of these equations, so I'm going to plug in right here z equals 3 into this, simply because my numbers are smaller than that equation. And I wind up with x plus 2 times 3 equals 8, x plus 6 equals 8, so x equals 2. Now that I know x and z, now I can plug them into one of my original equations and figure out what y is. I'm going to plug into this bottom one just because my numbers are smaller. So I have 3 times 2 minus y is what I'm looking for, plus z, which I know now is 3, equals 9. So 6 minus y plus 3 equals 9. 9 minus y equals 9. So minus y equals 0. So y equals 0. So I know my x, my y, and my z. And don't forget, they are ordered pairs. So my answer is 2, 0, 3. Meaning x is 2, y is 0, z is 3. Okay, let's try that again one more time. All right, first thing I want to make sure is that they're all lined up correctly, and they are here. And then I'm going to decide which variable to eliminate. Okay, I like the looks of this one. They're all pretty easy. Hey, these two, the y would get eliminated right away. I'm going to change my mind and go with eliminating the y's because I can just add these two together. And then I can add these two together by just multiplying this one by 2. Think about eliminating the same variable in all three equations. All right, so my first step is 2x plus y minus 3z equals 0, and x minus y plus z equals 0. My y's get eliminated, and I wind up with 3x minus 2z equals 0. All right, now I have to use this equation, but I can use either one of the others I want. So I'm going to use this one where they already have opposite signs, and I don't have to mess with signs. Just going to multiply everything times 2. This one's going to get me 4x plus 2y minus 6z equals 0. And down here, I'm going to have 2x minus 2y plus 2z equals 0. So once again, I've eliminated that same variable, giving me 6x minus 4z equals 0. This is another case where I might notice, hey, I can make these numbers smaller in my equations, right? 3x minus 2z equals 0. And I notice that I've got the exact same equation, right? So I can tell from that that it's going to be an infinite number of solutions. Let's say I missed that and I'm thinking, oh, I'm going to eliminate these z's. I would need to multiply one of them by -1 so that when they get added together, the z's get eliminated. I would have negative 3x plus 2z equals 0, and not only did my target z's get eliminated, but so did my x's, and 0 equals 0 means infinite solutions. Right? Something crazy like 5 equals 0 means no solution. Right? That's not what we're talking about here, but just to remind us. Otherwise, you get something like x equals a number, z equals a number. If your variables disappear, it's either no solution or infinite solutions. All right, so if I have infinite solutions, and let's say we're going to leave z arbitrary, the last one arbitrary, that means my answer is going to look like this if z is arbitrary. I just have to go up and solve an equation where I get x equals something with only z in it, and y equals something with only z in it. Here, with this equation, I can get I can solve this for x and get x equals something with z in it. So let's do that. Okay, remember I'm solving for x. X is what I don't know. So if I add 2z to both sides and divide by 3, I get that x is 2/3 z. Okay, that's what x is. So 2/3 z. Okay, now that I know that, I'm going to take one of these original equations, and maybe I'll do this one on the bottom because my numbers are smaller. And I'm going to plug in what I know x to be in terms of z, and then I can solve it for y. So if x is 2/3 z, I'm going to replace that x with 2/3 z. Minus y is what I'm looking for, so that's okay, plus z equals 0, and solve this for y. First thing I'm going to do is get rid of that fraction because I have an equal sign. Okay, so times 3, times 3, times 3, times 3, giving me 2z minus 3y plus 3z equals 0. 5z minus 3y equals 0. I'm solving for y, remember? Keep in mind our goal, solving for y. So divide by negative 3 to get that y is 5/3 z. So now I can put that in my answer. There is an infinite number of solutions and they fit this format. So you can find as many solutions as you choose. One of them is if z is 0, 0, 0, 0. If z is 1, x is 2/3, y is 5/3. If z is 2, x is 4/3, y is 10/3, etc., etc. Okay, let me know if you have questions.